Great. I think we're almost at quorum. So just before jumping into the content, I'll give you a quick overview of the specific pieces that we're going to run through. Firstly, starting off about kind of the traditional approach to descoping PCI and managing card data, which is tokenization. It's a term that's taken on a lot of different meanings in the past few years. There's obviously card and sensitive data tokenization, but in general, kind of payments and financial infrastructure, it's got a lot of different meanings. So we're going to be talking about the card security version of tokenization, as well as the kind of main drawbacks and some of the bottlenecks that people encounter when they start rolling out traditional tokenization as well. We're going to run through encryption. Encryption is a very, very broad surface area, and it's where Evervault as a company got started. So we're pretty familiar with that side of things, but we're going to apply it specifically to card data and sort of touch on the PCI aspects of card data encryption as well as the approach that we follow to encryption, which is what we call dual custody encryption. The most useful part of these webinars is typically in the kind of both Q&A, but also gotchas and top tips, where we talk about some of the things that people encounter as they go live, or a few months after they go live, where they encounter various issues and quirks of all these different architectures. So we'll try and make that as pragmatic and practical as possible. But without further ado, to run through what tokenization is, it's a conceptually pretty simple idea where sensitive payment data, or any data really, but we're talking about this from the perspective of card tokenization. You take a PAN, or the 16-digit card number, and a CVV. You send that off to a third-party vault provider who stores it, and then they're responsible for all the kind of security and compliance aspects of that data. And in exchange for them storing that data, you get back a redeemable token, which is typically kind of a long random string, almost like a cloakroom ticket, where at any point in the future, you can send a request back to the vault to redeem that data and get access to the raw card information, or the raw sensitive data. So it's sort of a three-step process. You've got the card collection, you've got the card storage, and then you've got the card retrieval at a later date when you want to process a payment. But in practice, you're pretty much entirely outsourcing all of the responsibility for storing that data and then making sure that it's secure and compliant. So you can kind of not worry as much about that. But it is a third-party database. In practice, it's a very, very standard architecture. They'll maintain database infrastructure. They'll handle all the kind of global distribution of that, availability and scalability and so on. And then they'll make sure that everything is stored as securely as it can possibly be. When you get to the point that you have a token and you want to process a transaction, which is obviously the reason that you want to kind of keep cards in a vault, typically this would be for a card on file use case, where a consumer might have a wallet containing their card information, or maybe you're a recurring business where you're processing a transaction for a subscription or something similar every month. How that works with a token vault is you process the transaction initially by taking the token that you've stored in your database. You send it to the token vault provider alongside instructions on what to do with that token once it's been collected. The vault provider searches their database for that token, they retrieve the raw card information, and then they forward that on to the payment processor or any other third party that you might want to send that card data to. So from the customer's perspective, and the business that's integrating with the token vault, they're only ever managing a token. And then between the vault and the payment processor, all of that information is exchanging raw card data, which is obviously fully in scope for PCI, as well as just the general security implications of that. You'll see in this diagram that the database lookup is a pretty crucial part here. Typically a card record, you're looking at something like a kilobyte. So you're not just storing the 16-digit card number in the vault. They're probably enriching that with other types of data, like the BIN information, so information on the issuer, timestamps, request headers to show when that token was created and who it was created by. But effectively, they're looking up their central database, retrieving it, and that introduces sort of some amount of architectural complexity that we'll get to in a second. We're not going to focus too much on tokenization for this webinar, and instead it'll be looking at the encryption side of the house. But some of the pros and cons of tokenization, I've alluded to a couple of these already, but one of the major pros is that it truly is just full outsourcing. So what would have been your problem if you're managing and storing card data yourself, you can just totally offload that to a third party, and you can effectively wipe your hands of that data, where if it does get breached or there's any kind of compliance questions, you can typically rely on the vault provider to look after all of those for you. The other advantage that isn't necessarily a technical advantage, but it is just an operational advantage, is that it's standard. Since 2004, when PCI DSS version 1 came out, tokenization has been a pretty accepted way of doing PCI descoping. And it was actually standardized as part of the PCI guidelines in 2011 as well. So not only are kind of most businesses familiar with how to do card tokenization, most of the PCI and security and compliance community are as well. It's what most PSPs do, especially when they want to keep all those cards in file and implement some version of card management with token provisioning and card and file use cases as well. It does have a lot of cons though. So we'll kind of touch on these in a little bit more detail shortly, but speed is a major thing. Conceptually, it's very simple that there is a database containing all of the raw card information, but because there's a central database, there's another service that needs to be called to handle all the tokenization operations. So creating the token takes time, retrieving the token takes time, and deleting the token takes time. That introduces latency into your payment flow, which maybe for a recurring business isn't a huge deal, but if you've got a standard kind of consumer checkout flow where every second matters and conversion rates get impacted if a payment process is slow, that latency just compounds, because typically it's not just going to be one operation, especially for a guest checkout use case. You're probably going to create the card, detokenize the card, and then also delete the card token after the transaction is done. So if you combine that, you're adding multiple seconds onto a payment transaction. The second piece is risk. So from your perspective, at least legally and contractually, you're outsourcing a lot of this, but it centralizes availability risk, which is arguably or at least statistically, it's a more important factor. The odds of a data breach, and in practice, data breaches don't happen super often, thankfully. But availability is a much bigger issue, where because there's one central vault containing all of this card data, the availability of that vault is extremely important for all of your payment processing. So it centralizes all of the risk for handling those payment operations into a single piece of infrastructure that you've no control and visibility over. And as a result, when there's an outage with the vault provider, typically there's also an outage with payment processing, unless you've implemented a multi-vault strategy, which some larger companies will do, but the vast majority of companies that are looking at doing card tokenization typically don't, both for complexity and cost reasons as well. And then the final thing is just the economic aspect. Because there's a database that costs money to run, it costs money for storage, and costs money for all the operations that you do on that data. Not only do they incur costs when you actually process a transaction, but simply storing a card and file costs money, as well as deleting the card as well. So again, for those guest checkout use cases where you might have 3 interactions with a single card or a single token, it typically just ends up being much more expensive, because the fundamental architecture means that the vault providers have more cost for managing all that data, and they'll typically pass that through to the customer as well. So it's something to be very conscious of, especially for those use cases where you have a lot of cards, but the frequency of interaction with those cards isn't particularly high. The other approach that some companies have taken, especially when they're building this infrastructure in-house, is encryption. I'm kind of greatly simplifying all of the kind of mathematical concepts of encryption here, just because I don't think it's particularly relevant. But symmetric encryption, which is the version of encryption that most of us are familiar with, is a process of taking a piece of sensitive data and you split it into 2 separate pieces. One is the key, which is the very sensitive piece of information that's used to effectively unlock or reverse the encryption on that piece of data, as well as the ciphertext, or the data that's been encrypted using that key. So you're effectively just kind of splitting the responsibility for the security of that data into 2 pieces. In a lot of cases, most companies that are implementing encryption themselves are probably storing the data and keys in the same place. And you end up in a situation where the encryption itself is pretty useless, because once you have the encrypted data, once you have the key, you effectively have the original plain text data as well. Rolling out encryption is also notoriously difficult. There's sort of a famous adage in software engineering, which is don't roll your own crypto. It's totally true. It's an extremely easy thing to get wrong, and even very, very sophisticated engineering teams make mistakes that look small, but in practice, they totally undermine the entire security of the whole piece of infrastructure. And that's typically because the key itself is hazmat, as we like to call it, and it needs to be stored somewhere securely, which you could also just store the raw card number in that place if you do have good key management infrastructure. but also some of the mathematical and cryptographic exploits are a lot more sophisticated than most software engineers are spending time thinking about. So it's very, very difficult to implement correctly. And typically it makes a lot of sense to not even think about it. But effectively with symmetric encryption, if you have access to the key, encryption provides little value. You're just splitting the responsibility. And without access to the key, so if you lose the private key, but you have the ciphertext, the data itself is irreversible, at least practically speaking. And we'll get into some of the kind of theoretical edge cases on encryption later on. Some of the other problems with traditional encryption, outside of just the key management piece that I spoke about, is the PCI guidelines earlier on had referenced the idea that encrypted card data was not considered out of scope for PCI. And this is one of the things that companies that are considering using encryption for PCI scope reduction reference frequently. There's a publicly available FAQ 1086 in the PCI or on the PCI website that explicitly says card data is not considered out of scope. And as a result, a lot of people tend to veer away from it. As well as that, as I mentioned, rolling your own encryption is extremely dangerous. And as a result, that complexity is something that sort of veered people away from using encryption to secure card data towards tokenization, which is frankly harder to get wrong, but also kind of more commonly accepted as a result of that as well. The other piece is with traditional encryption, and I'm talking specifically about the other form of encryption here, which is asymmetric cryptography or public key cryptography. Exchanging encrypted data with third parties is a major headache. With symmetric encryption, like I mentioned, you're splitting the piece of sensitive data between the ciphertext and a sensitive private key. Whereas a public key encryption, there's three components. There's the encrypted data itself. There's a public key that is designed to be obviously public, and that can only be used to encrypt data with. And then there's a corresponding private key that maps directly to that public key that needs to be stored securely. And in that case, it means that you would kind of have a public key yourself that you expose to your customers that allows you to collect that data and have it encrypted. That produces the ciphertext. And then you send the ciphertext to the third party who has the private key to decrypt it. So as you can imagine, not only technically, but also organizationally, this just gets extremely difficult to manage because you have two parties that need to manage their components of the encryption keys. Those keys need to be rotated frequently. And if you're not a major customer of a PSP, for example, even getting them to configure this infrastructure can be very, very difficult. So traditional encryption in comparison to tokenization is, generally speaking, just not the best choice. And there's a lot of architectural changes that need to happen to make traditional encryption make sense for card data. So this is a good segue into what we call dual custody encryption, which solves a lot of the issues with traditional encryption, provides a bunch of advantages, and also kind of maps more neatly to the traditional model of doing card tokenization as well. Dual custody encryption is, like I mentioned in this asymmetric cryptography example, where you have a public key and a private key. It's that, but fully abstracted. So in this diagram here, you'll see that we're taking a piece of sensitive data, we're splitting it into the encrypted data or the ciphertext, and then encrypting it using the public key, which is exposed publicly, in our case, through Evervault. Evervault is then responsible for managing the private key that can be used for decrypting that data. And then we act as basically like a broker or intermediary between you and third parties. So no third parties that you need to send data to ever need to worry about managing any of this encryption stuff. They just receive the raw card data. So dual custody encryption is traditional public key encryption, but with shared responsibility through a third-party service provider. In this case, Evervault, but this model could in theory be implemented by any payment processor or any token vault. And the simplest way of kind of distilling this down is from a security or threat model perspective. You store encrypted data, and then Evervault stores encryption keys. And we'll talk a bit about some of the advantages to that in a few moments. For companies that have rolled out tokenization before, either through their PSP, where the standard kind of payment iframe approach is used, or through another traditional token vault, typically card collection, especially if it's a consumer-facing product with a web page or a mobile app, they'll take the iframe approach, where the PCI Council released guidelines for SAQA, which is the simplest self-assessment questionnaire in PCI, where if you can assert that the card data is only collected inside an iframe, which is effectively an embedded web page within a web page that's served directly by the PCI compliant service provider, either a PSP or a token vault. That iframe is loaded, card data is entered there, and traditionally that card data is then sent to the token vault, like we showed in the other diagrams. With dual custody encryption, the implementation is very, very similar from a customer's perspective, but under the hood, the operation for securing that card data is fundamentally different. So what happens is an iframe is loaded. It looks and feels pretty much the exact same as you would get from a PSP or a token vault, except when the user types in their card data, instead of sending it off to a third party to store and manage, the card data is encrypted directly on the user's mobile or desktop computer. So there's no network requests at all. The public key is just loaded when the web page loads. It's static. It doesn't change very often. So there's no need for API calls or anything like that. And then on every single key press, the card data can just be encrypted in microseconds, taking advantage of some of the hardware acceleration that you'll see on pretty much all modern web browsers and mobile devices as well. So once the card data is encrypted on each individual key press, the encrypted data is served back to your code, and then you can send that directly to your backend. There's no need for a network request to store it with the vault or to any other third-party service. And as a result, there's no infrastructure costs, which has a bunch of pricing advantages as well. So looks and feels the exact same for the developer that's implementing this, as well as for the consumer that's typing in their card data, except if you go in the weeds and you look in the network tab, you'll see when the user types in their card data, no network requests happen. The card data is just encrypted natively and handed directly to the developer's code. Once you've collected that encrypted card data, obviously you need to send it off to a third party. And like I mentioned with traditional public key encryption, that's very difficult if you're relying on another third party to do the decryption for you. So how we manage it and how kind of a dual custody implementer should manage it is that the encrypted card data is sent to the dual custody encryption provider inside an isolated environment. In our case, we use AWS Nitro enclaves, which are kind of like data clean rooms where you can attest that there's no network requests that are possible from inside that enclave. And you can verify that the code running in that enclave is the code that you wrote and signed using your certificates. In our case, we receive the encrypted card data. We grab your 32-byte decryption key. So this is the private key in public key cryptography. That's loaded from memory. So there's no database lookups required because they're so small. So even with millions and millions of customers, you can load all of this key material inside the enclave, and you don't need to worry about any of the scalability aspects just because the key material is so small. Data is then decrypted in real time, again with hardware acceleration, except instead of on the consumer's device, it happens on the server. And once the data is decrypted, it's forwarded directly to the payment. It's forwarded directly to the payment processor using a network proxy. Once the data has been decrypted, it's deleted. The data only exists in plain text for a few microseconds as that request is being sent to the third party. And from an implementer's perspective, the only infrastructure change is instead of sending an API request to, for example, api.stripe.com, you get a new domain name from the proxy. The request payload stays the exact same. The response payload stays the exact same. And then the only thing that the proxy does is it swaps out the encrypted card data for the decrypted information. So it's much, much faster. The implementer only ever stores encrypted card data, and then the data is discarded once it's been sent to a third party. So at no point does that ever get persisted, either in a database, in logs, or in any of the other observability tools. There's a bunch of reasons why this model is better. And again, if anybody has questions as we run through this, feel free to shoot them in the questions tab in Livestorm. But fundamentally, payment infrastructure needs extremely high uptime. Every single dropped request is a dropped payment. And especially in, for example, B2B use cases or any high value transactions, every dropped request is potentially thousands or tens of thousands of dollars in lost revenue. So the SLAs that you should expect from a payment processor are extremely high. And you should also expect that of any other critical path third parties that are in a payment flow. Like I mentioned before, when a token vault fails, your entire payment operation fails because you're depending on that entity being up to look up your raw card data from the token in the database. There's multiple pieces of infrastructure that need to be available, and just scaling and managing that infrastructure is extremely difficult. What dual custody encryption lets you do is there's a few other pieces, but the two core things are true multi-region deployment. With a traditional token vault, if you have, say, 1 million cards on file and you're adding, thousands of cards a day or a week, maintaining synchronization for multiple token vaults across multiple geographies or cloud regions is extremely difficult. And no token vault provider actually does this in practice. Typically, it's sort of an active failover approach where you have the primary vault. If that fails, there's a backup that gets manually recovered, and there could potentially be other infrastructure that can be spun back up. But that typically takes minutes or even longer if it takes a while to react to the incident. With dual custody encryption, because no matter how big, if you're storing one card or 10 billion cards, the only piece of information that needs to be replicated globally is that 32-byte public or private key. So very easy to replicate globally. Every single card that gets encrypted doesn't need to be synchronized because we're not storing it. So you can deploy, and we do deploy that infrastructure in multiple regions and multiple availability zones that are totally isolated. And it means you get full active resiliency where at any one point in time, all of the regions in the cloud are active, and you're just routed to the fastest region based on latency routing as well. The other advantage is load performance. So on the point of vault scale up, as you're collecting more and more cards, that database gets bigger and bigger. Database lookups take longer and longer, and just the storage costs as well as the kind of compute costs of using that data just get bigger as your business grows as well. With dual custody encryption, because the key is just maintained in memory, if there's one request or 10,000 requests, the latency doesn't change at all because there is no third-party network request to a database that gets bottlenecked somehow by the load or any of the throughput that's happening. So you get much better guarantees around consistent latency and performance, no matter how big your business is. The other advantage is security as well. And it sort of wasn't intentional that security was second here. I just think for a lot of companies, security is considered a tail risk. So it's never kind of the core consideration, but it's definitely in the top three. This is, in my opinion, the biggest advantage of dual custody encryption versus the token vault. But dual custody encryption, in the same way that it improves performance and availability because of not having a single point of failure, it also helps a lot with security for the exact same reason as well. So there's distributed risk where with a token vault, all you have to do is compromise the vault itself where all of the card data is stored. Whereas with dual custody encryption, because you're storing the encrypted data and the dual custody encryption provider is only storing encryption keys, for data to be breached, both the tokenization or encryption provider as well as the customer that's storing the card data need to be breached simultaneously for data to be breached. So you can mathematically look at that as, if there's a 0.001% chance that a business gets breached in any given year, you can effectively square that because the odds just get much, much lower that both of those mutually exclusive events happen at the same time. The second thing is temporary access. So because the plain text data with dual custody encryption only exists for microseconds, you don't have to worry about, even if the infrastructure does get breached, all the card data only exists for a few microseconds in a secure enclave. So there's a tiny attack window, even if there was potentially a malicious attacker, but in practice, typically it's misconfigurations or just poorly implemented security policies that cause most of these issues as well. So there's a bunch of very, very major security advantages to dual custody encryption that traditional tokenization just doesn't offer. The other thing is speed and performance. The kind of simple analogy for this is with a token vault, you kind of have the token, you go to the token vault, you ask them to find your data, they run a database query, they retrieve it, and then hand it back to you. Whereas with dual custody encryption, you already have the encrypted card data on hand, and we already have the key in memory. So to decrypt that information and pass it on to a third party, it's just a single pass-through request without any other database lookups. And as a result, because of that kind of fundamental architectural difference, every single request for either encrypting or decrypting a card number is typically 200 to 300 milliseconds faster. So again, if conversion rate or checkout performance is an important aspect, you get a lot of very nice advantages that also kind of clean up a lot of your infrastructure as well. So because there's no extra network calls for encrypting the card data, that shaves a network request, even if that network request was very fast. you're eliminating 200 to 300 milliseconds of latency when the user kind of clicks the checkout button and types in their card. There's faster retrieval because all we're storing or all we're managing is the tiny decryption key in memory, rather than having to do a full database query for every single card that you want to decrypt. And then the third thing is it's obviously purpose built. So because we're not storing a generic token vault with a bunch of different card data, we can just implement a service that's specifically designed for fast key lookups using a key value store, which ends up being way, way faster than a SQL database or any of the other kind of traditional database models that a vault provider would use. And then finally, true data control is kind of the biggest aspect here from a kind of long-term resiliency standpoint. With the token vaults, because they kind of, I don't want to say they hold your data ransom, but they are effectively the ones that are managing and maintaining your store of millions of cards. If you want to migrate to another token vault or even just kind of have your own backup for resiliency, you're depending on their cooperation to migrate at any point in the future, which, if you're in the middle of a contract renewal or pricing negotiation, you can lose a lot of leverage there just because, they have all your card data and you don't have a backup of it yourself. With dual custody encryption, because you don't need to kind of continually update the backup every time that a new card is added. If you did want to do a backup with a vault, every day or every minute, for example, you would need to kind of create a new backup that contains all of the new cards. Because the keys to decrypt dual custody encrypted card data are static aside from kind of medium-term key rotation, you can use escrow back to exit. So when you open up an app on a dual custody encryption platform, the master key or even kind of cryptographic shares of that master key can be stored with a third-party escrow provider who has contractual provisions in place that allow you to get access to that key in certain scenarios. It means easy recovery in the event that you do want to migrate away from the dual custody provider, as well as just kind of almost an insurance policy where, worst case scenario, if you needed to fail over to your own infrastructure, you can just immediately retrieve the share of that private key and start decrypting the card data yourself. Pricing and economics are kind of slightly different because, again, the kind of cost implications of the different architectural models are different based on storing the card data every single time you add a card versus just storing a static card. You'll typically see this in pricing proposals that you get from vault providers as well. There's a bit more nuance to it than this simple table, but in practice, because there's no infrastructure costs, and in fact, we don't even know when a card is encrypted, with dual custody encryption, there's no cost for encrypting data. So if you have a use case where you're collecting many, many cards, but you don't know for sure when those cards are going to be charged, it's a much more friendly pricing model because you're not paying based on the size of your card database. You're just paying when you get value from the product itself. So in summary, token vaults will typically charge for tokenizing or creating the token. They'll charge for detokenizing, which is every time that you process the transaction, as well as deleting the token, which is interesting because they incur infrastructure costs every time that you want to delete something, and that gets passed on to you as a customer. Whereas with dual custody encryption, because there is no database and there are no costs for either encrypting or deleting tokens, and the dual custody provider doesn't even know that that's happening. The only point that you get billed is when you get value from the card data, or in other words, when you're actually decrypting a card and processing a transaction. Moving on, I know we have a few questions in the question section, which I'll get to as we approach the Q&A, but there's kind of two major topics that kind of face a lot of pushback with encryption versus tokenization. So I thought it would make sense to just run through some of the common gotchas as well as top tips with companies that are using dual custody encryption in production. The first of them is this kind of common rebuttal that encrypted cardholder data is in scope for PCI. I kind of alluded to this earlier on, but PCI FAQ 1086 that I referenced explicitly forbids or kind of it claims that encrypted card data does not eliminate the need for that environment being in scope. So this is a direct quote from PCI FAQ 1086. And as a result, it's just led many companies to veer away from encryption as a descoping mechanism. Encryption in and of itself, the spec is totally correct, is not enough to reduce PCI scope. And as a result, that's where some of the dual custody advantages come in and kind of combat that with a second FAQ, which is published a little bit later called 1233. So this permits the architecture for third-party service providers, in other words, us, where basically if you're a third-party service provider receiving or storing data encrypted by another entity, and you don't have the ability to decrypt that data, or simplistically, if you have the encryption keys to delete that data, it is in scope. But if you don't have access to the decryption keys, then it's not in scope. So this is the kind of baseline that we rely on for our security model, as well as the kind of compliance posture. And that's been reviewed by third-party QSAs as well. But outside of that, with those opinions, the PCI scoping setup is pretty much equivalent between traditional tokenization and dual custody encryption. As long as you're using an iframe and you're not handling the card data in plain text at any point, then you're eligible for SIQA as a merchant, which is the simplest self-assessment questionnaire. As well as if you're a service provider, you now have to do an SIQD, but the SIQD is heavily descoped to a set of controls that's not directly equivalent, but pretty close to what you would get with an SIQA as well. So heavily reduced scope from hundreds of controls down to a couple of dozen, depending on the exact architecture. The second piece, and this is kind of a personal interest of mine, is that many people assume encryption is reversible while tokenization is not. Encryption is obviously reversible if you have access to the decryption keys, but if you don't have access to those, there's a couple of interesting points of nuance here. The first is that traditional payment tokens, where you're relying on a third party, because they can effectively create a token that looks like whatever you want it to look like, they'll generally speaking return you a token that retains parts of the original card number. So the BIN, for example, the first 6 to 8 digits will remain the same, as well as the last 4 digits, so you can keep the token recognizable. And if you look at this kind of statistically, that means there's only 4 digits to guess in a 16-digit card number. The last digit is a checksum, and then doing a brute force attack means that there's really only a few thousand or 10,000 possible combinations for a card. So it introduces a lot of risk, especially if you're dealing with corporate cards with high spending limits. Using statistical analysis to derive those raw card numbers is extremely practical and something that you see a lot with card testing attacks, for example. It's pretty easy to use third parties to verify that a card is legitimate, especially with high throughput if they're using dedicated services like 3D Secure or network tokens, for example. With dual custody encryption, it's very different. This is a slight drawback of using encryption, but if you tokenize a card number traditionally, you give it 16 digits of a PAN, you'll typically get a 16-digit card number back. So it's about the same size. With dual custody encryption, the ciphertext of that card number or the encrypted card number is a lot bigger because you're storing the fully encrypted representation of the entire PAN, as well as a temporary public key as well. So what was a 16-digit PAN is now quite a bit longer. It's more like 40, 50 characters or so. But the advantage of that from a security perspective is it removes all of the structure and patterns around that encrypted card number. So if you encrypt the same card number 3 times, you'll actually get 3 different ciphertexts, and you need to rely on another approach for deduplication, like using fingerprints or something. But that basically means it's hugely resistant to brute force attacks. And that's where some of these kind of examples get pretty interesting. So using ECDH and AES 256, ECDH is elliptic curve Diffie-Hellman. It's the kind of probably the most popular form of public key encryption. It's used by Bitcoin, for example, as well as TLS in your web browser every time you open a web page. And then AES 256 is a pretty well-established, the most well-established symmetric encryption scheme. So this is how the internet itself is already encrypted. But to brute force a combination of these 2 encryption schemes, an attack would need 10 to the 17 years using 100,000 of the world's fastest GPUs, if you could get your hands on them. Obviously, a bunch of the LLM model trainers and providers are fighting pretty hard to get access to those. But 10 to the 17 years is 100 quadrillion in non-scientific terms. So it's a pretty long time, 7.2 million times the age of the universe. The other alternative to breaking encryption is using a large-scale quantum computer. If that did exist, and it actually does look increasingly likely that that could occur in the coming years, I think most of the people with resources for quantum computers would likely focus their efforts on stealing the million or so Bitcoin in Satoshi's Bitcoin wallets rather than a $100 credit limit card. That being said, that's not kind of a reason to not consider post-quantum encryption as an issue. So there are now new standards to replace elliptic curve Diffie-Hellman with post-quantum standards. NIST kind of finalized their standardization process a couple of years ago, and those kind of schemes are now being rolled out across the web that will make all these attacks totally resistant to quantum computers as well. In contrast, a token vault is just a centralized database of sensitive mappings. So you don't need any of this advanced tech to get access to the plain card information. So if a vault provider is breached, or what's much more common is there's a developer misconfiguration on logging or authorization, or even just somebody has access to AWS services they shouldn't, raw data can be exposed both intentionally and unintentionally. And kind of the knowledge of that happening, typically you see it with a lot of major data breaches that get announced. In some cases, they're announced pretty quickly, but in many cases, companies don't realize for months or even years in the worst case scenario that card data has been breached. So as I move on to the Q&A, I just wanted to flag that we'll be sending out a quick poll. If anybody's interested in getting more in the weeds on dual custody encryption or tokenization in general, feel free to click yes, and I'll set up a time to chat with you. But I know there's a few questions in the chat that have been covered already, but let me just take a look and see what we should run through here. So with a network token, network tokens are different, where they actually use traditional network or traditional tokenization. It's just the vault providers are managed and issued by the card networks themselves. So Visa, MasterCard, Amex, and Discover all maintain central token vaults. But the idea is that network tokenization would be a separate step to the standard dual custody encryption. So as a customer, you would store the encrypted cardholder data yourself. And then at the point of transaction, you would send a request to the token service provider from Visa or MasterCard, for example, to handle the rest of the transaction. The big distinction between network tokens and traditional tokenization is, aside from a bunch of other implementation details, network tokens are irreversible to the entity or the developer that's actually creating the network token. So the only services that can actually detokenize a network token are the issuing banks themselves during payment authorization. So they rely on kind of heavy authorization where you need to be directed to the core VisaNet or MasterCard network to detokenize a network token. But interestingly, yes, the token service providers from the card networks, they are implemented in the traditional tokenization flow, which is sort of partly a timing thing. Network tokens have been around for just over 10 years now after the launch of Apple Pay in 2014. So dual custody encryption just wasn't really a thing at that point. Adolfo had a question about key rotation and how that applies to dual custody. PCI itself doesn't mandate it, but as a piece of well-implemented security infrastructure, absolutely key rotation needs to be built in. You don't have to do it this way, but the way we manage it is we actually generate an ephemeral key pair for every single piece of card data that gets encrypted. So key rotation sort of automatically happens on every single encryption. That being said, there is an app master key that gets managed by the dual custody provider that should and does get rotated on a less regular basis. So unlike in the scenario where with traditional tokenization, there's a new piece of data created for every single card. With key rotation, typically best practice would be to do that every 90 days if you're extremely security conscious, or maybe every year if you're less security conscious. It still ends up being an extremely small set of data. So you've got 32 bytes for each key. If that doubles to 64 bytes in 90 days or in a year, it's really not a huge deal from a storage or migration perspective. Some of the other questions look like they've been answered, but if anybody has any questions about encryption broadly, whether that's related to card data or not, or traditional tokenization, feel free to shoot me an email, shane@evervault.com. And yeah, for those of you who've requested a call, I'll be in touch shortly. But other than that, thank you for joining our webinar, and hopefully we'll see you on the next one.